welcome to day 2 of the 12 Days of LiDAR. My name is Alex Billick, and today's topic is going to be covering typical LiDAR derivatives. So recall from yesterday that you now have an understanding of the terms used in LiDAR when we're using the lingo. So what we're going to focus on today now is derivatives that come directly from the point cloud. We're not going to be focusing on anything that maybe requires some ancillary data or anything like that. We're just going to be taking things that are your typical derivatives when we get a LiDAR point cloud. Those are going to be a canopy height model, digital surface model, and a digital elevation or digital terrain model. For today's exercise, we're going to be using a tile from the recently acquired provincial forest inventory LiDAR data in Ontario. If you'd like to follow along, you can go to Ontario GeoHub and then look up the Forest Resource Inventory Leaf on LiDAR. And when you come to this map, you're going to see all the coverage. And the area I'm going to be looking at today is Lakehead University campus. So we're going to zoom down. And when we zoom down to a certain extent, we actually get this grid appearing. And then I'm going to keep zooming down here. You see campus is here. And when we click on it, we get prompted with these different download links, and we can actually see what is available. The standard height above datum point cloud. This is your non-normalized LiDAR. So this is from the sensor. We haven't accounted for terrain or anything else. You can download that in LAZ format. It's a special type of LAZ called COPC, which is a cloud optimized point cloud, which means it's made for online delivery. We have a height above ground point cloud. That's the normalized point cloud. So you can actually download 2 versions of every point cloud, and then you can download 3 raster products in GeoTIFF format. A digital terrain model, DTM, digital surface model, a DSM, and a canopy height model, a CHM. So if you'd like to download these, you can follow along with this tutorial, and you get a sense of what this data looks like. So I'm just going to close that for now, and I'm going to open those point clouds. Now, in a later one of these episodes, I'll be talking about different types of LiDAR viewers. For today's purposes, I'm going to be using one called PoTree Viewer, but you can follow along or keep the data and then look at it when we go through that. So when I zoom out, I can see the entire extent of the tile, and it looks good. If I click on it, I can change and colorize it by classification, or I could colorize it by intensity if I'd like to. So I can start to explore some of these different pieces of information. I can look at it by elevation, but I'm just going to keep it on classification so we get a bit of context here. So dark green is vegetation or buildings, blue is water, and you get a sense of everything else here. Now, if you're wondering, is this a normalized or non-normalized point cloud, the way to tell is we can actually drop down to the side here, and we see that there's drop off here in the terrain. I can zoom in. So this has not been normalized. What I'm going to do is I'm going to use a tool here that lets me take a profile. So I'm going to just take a profile across a group of trees here and say show 2D profile. And we see now that as we move our mouse along, it jumps point to point, and this tool will report to us the XYZ, and it's the Z values, the elevation that matters to us. So we see that yes, this has not been normalized, and our tops of our trees are, say, 222 meters above sea level, and our ground is 202 meters above sea level, something like that in this particular spot. The first derivative out of this LiDAR data is what's called a digital surface model. And what a digital surface model represents is the highest point that was encountered by the LiDAR signal at every point where a point was collected. So they represent the entire surface of the Earth and all objects on it. And these are derived from the first return. So they're the highest elevation points are compiled from the LiDAR to create a continuous raster that depicts the topography and all objects on it, and that's called a DSM. By contrast, the DTM, or digital terrain model, is all the ground points, or the last returns. So just from this point cloud, we can create a digital surface model and a digital terrain model. And so that gives us 2 rasters that represent what's going on the Earth's surface. But from a forest management perspective or engineering or somewhere else, that isn't always entirely useful. Sometimes what you really want is a raster that represents how tall features actually are. Well, if you're following along, you can probably guess how we determine that. If we take the Earth and we subtract the height of the Earth at that point from the DSM, from the highest point, we can figure out exactly how high each object is, and that's what your canopy height model does. I'm going to open in QGIS here the three products. So we've got our DSM, our DEM, and our canopy height model. If I zoom into an area here and I click on it to get the information, we're going to look over here at the identify results section. That's the important one. So we see that our digital surface model at that particular point was 223.4 meters above sea level. Our DEM at that point was 204.5 meters above sea level. If we look at our canopy height model, we see that it is just the mathematical difference, and you can subtract these to confirm it for yourself, but it's 18.9 meters tall. So the canopy height model is created by taking the digital surface model and subtracting the digital elevation model. That's the basic logic going on here. So it represents things really well. However, if you're thinking through this process, where could we get some potential problems and noise? Well, the problems that can arise are when we think something is ground, but it's actually not. And that is a significant challenge in forestry. We have forest types where we might have a very dense understory that might not be that high. It could be a shrub layer of a meter or two, or it could be a balsam fir understory that's several meters tall. The problem is if we don't understand how this canopy height model is created, we might inadvertently trust a data set and subtract a digital elevation model from a digital surface model and end up with a canopy height model where we've actually lopped off several meters of height from those trees. And that has big implications in forest management. So it's very important to understand the accuracy of our DEM and make sure that it's accurate. Now, the digital elevation model, I make it sound like it's as simple as saying the last return, we just treat all of those the same, and we just turn that into the ground. And that's not the case. There is a filtering process where we try to remove noise and we try to remove those errors. We try to inspect the data to really understand what's going on. But that doesn't mean errors can't happen. So it's very important to understand. And if you see heights in an area and you're wondering, what's going on here? Does this make sense as a land manager or forest manager? Do I trust what's going on in my canopy height model? You can come back to these raw data products like this and inspect the uncorrected LiDAR point cloud and see, am I seeing some sort of a mid canopy here? Am I seeing a big jump that maybe just didn't get caught? Do I have concerns about this? Because maybe I can correct it. The other thing that you can do, and we'll jump over to QGIS for this, ARC will do this as well, is we can actually go into the properties of our digital elevation model and we can change it to what's called a hillshade. And what a hillshade does is it basically acts like a flashlight. So we can kind of highlight what's going on. And you can see here the artifacting from the buildings. You're going to get this. This is very typical of what's called a triangulated irregular network, a way of filling in some of these gaps and interpolating when we've got big elevation changes and there's a big gap there. And that's perfectly acceptable and normal around buildings. We know that's going to happen. What we're looking for, though, is in those forested environments. So, right along the river here, for example, is a forested environment. We can see, and it doesn't like me zooming in too much here with the streaming software, but if you do this yourself, you'll be able to see it. There's a lot more of that tin artifacting going on in this particular spot than there is anywhere else. And what that's likely caused by is some understory there where it was caught that that's not a correct ground return. So they were removed in a filtering process, and now we're using an algorithm to try to fill those gaps in. And there's some errors associated with that. So this is not perfect. But It's a way to inspect the data and try to get a sense of what's going on. Try to fill in the gaps and say, yeah, I can see what's going on here. This makes sense or this doesn't. Um, but what I want you to take away from this more than anything else is understanding the logic of how this is done and understand that we're doing this at massive scales. So in forest management, if we're talking about 1 million hectares plus of area, it's very challenging to, we're not going to go tile by tile. So there will be errors that filter through. But what you have the capacity to do as individual managers or data analysts is actually ask these questions and say, does this make sense? Did my stand just get shorter over a 10-year period since the last inventory? If that happened, I would be asking questions around my digital elevation model. Does it have some kind of error in it that's causing my stand height to drop? Because that could be the difference between a block that would make sense for saw logs versus one that's now going to go to pulp. So it's important to understand where this data product comes from. The other thing that's important to understand is that we can create different, there's different ways to take the point cloud and turn it into that digital surface model raster or that digital elevation model raster. The biggest thing that can impact it is how we fill in gaps. So you can run an algorithm that takes each point and turns it into a part of the raster. You can run one that's designed to try to fill in gaps. They all have trade-offs. None of them are perfect. So understanding what the assumptions are of the models you're using and understanding how some of those gaps may have been filled in may provide you some other insights to understanding your land base and say, is this appropriate in this forest type? What might work in the boreal may not make sense in the Great Lakes St. Lawrence or vice versa. Different ways that the crowns behave, different sizes of crowns, the resolutions, it may not be a one size fits all. So while we have excellent data products provided by the ministry as a baseline, individual forest managers may choose different resolutions that make more sense for their forest type based on trends that they start to see. So it's not that you need to be a LiDAR analyst to ask these questions. You have to ask the questions of, does the information I'm getting from this generally make sense, or do I have other questions, and can I maybe inspect a few samples of this in areas of walk the ground and see, yeah, if you have a stand on your forest where you know there's a really dense understory of balsam, go grab the LiDAR for it and take a look at it and compare those two, because that's going to give you the best calibration to understand how accurate is it in the worst case. And it's not that it's going to be perfect. Of course not. It's a large scale data product, but it's a tool in the toolbox. So I hope that gives you a little bit of insight into those three important LiDAR derivatives that you're most likely to encounter. And tune in tomorrow for understanding a little bit more about those LiDAR classes and how LiDAR is classified and different approaches to that so that maybe we can turn those buildings from vegetation into actually being called buildings. Thank you very much for listening.